Welcome to this lesson on geothermal energy systems. We will look into the deep geothermal systems and focus on direct use of geothermal heat. My name is Alexandros Danielidis. In this lesson, you will gain insight on how heat moves in the subsurface of the Earth and how direct use geothermal systems are developed for space heating. After completing this video, you will be able to describe the origin of geothermal heat, characterize deep geothermal systems based on the dominant heat transfer mechanism, understand geothermal gradients, discern the elements required for a geothermal system, differentiate between direct use and electricity production, and outline the direct use of heat in geothermal systems using two wells, what we call a doublet. So, what is geothermal energy and where does it come from? Geothermal energy is generated in the Earth's subsurface. A small part comes from the cooling of the planet since its formation more than 4 billion years ago. The largest part of heat in the subsurface comes from the decay of radioactive isotopes such as potassium and thorium. The decay occurs naturally and releases heat that radiates outward towards the surface of the Earth. The temperature therefore increases with depth, but also varies based on tectonic activity and heat transfer mechanisms. Now that we know where heat comes from, let's see what we need to have a geothermal system. A geothermal system requires three components: heat, a fluid to carry the heat, and a fluid pathway through which the fluid carrying the heat can travel through. Fluid pathways can be the pores of a rock or existing fractures in the subsurface. The fluid is in most cases water, but can also include other components such as gases. Previously, you have seen the different types of heat transfer mechanisms using the example of a pan with boiling water. So you now know that heat transfer can occur via radiation, conduction, convection, and advection. For the rest of this lesson, we will focus on conduction and convection. Geothermal systems can be classified based on the dominant heat transfer mechanism. In conduction-dominated systems, heat is only transferred via conduction. These systems are found in areas without tectonic activity. Systems like this are used to produce heat and are found in depths up to around 3 kilometers. The thermal power ranges between around 3 to 30 megawatts. Convection-dominated systems, on the other hand, exhibit an upward fluid circulation that brings heat to shallower depths or all the way to the surface. These are typically associated with tectonic activity. Due to the high convective heat transfer, electricity can be produced via a turbine. Power in these cases can be as high as 400 megawatts, while heat is also produced as a byproduct. Between these two systems, we can have the enhanced geothermal systems, where either the fluid or the fluid pathways are absent and are introduced during the engineering of the system. For all these cases, a minimum of 2 wells are required: one well to produce the hot water and another well to re-inject the cooled water after the heat is extracted. In recent years, the installed capacity of geothermal systems has been increasing rapidly. Direct use geothermal systems have almost 7 times the installed capacity of electricity producing ones. However, the produced energy difference between the two is only around 3 times. This is because we only need heat during the cold periods of the year, while electricity is used throughout the year. The World Tectonic Map outlines areas of tectonic activity such as the subduction of the Pacific Plate under North America, the rifting of the Arabian Plate from the African Plate, or the spreading of the Atlantic Ocean. Tectonic activity is closely related to increased heat transfer. Overlaying the two maps, we see a strong agreement between tectonic activity and heat flow. It is important to remember that heat flow is still present even in areas where tectonic activity is absent. Away from tectonic boundaries, conduction is the dominant heat transfer mechanism. This results in relatively linear geothermal gradients, like the type 1 you see in the graph, and can be found in locations such as A1, C, and E on this map. Together with tectonic activity, convective heat transfer dominates, resulting in sharper geothermal gradients like the type 2 in the graph. The shape can vary, but these types of geothermal gradients are encountered in locations A2, B, and D. Let's look at an example of direct use geothermal production from an aquifer. During geothermal production, a minimum of 2 wells are required, a doublet. one to produce the hot water and another one to re-inject the cooled down water after heat is extracted. Inside the reservoir, we have heat transfer through the rock pores via advection and convection from pumping. Heat exchange via conduction is taking place inside the fluid and between the hot rock and the fluid. In the simple example, we visualize how heat exchange takes place inside the reservoir using a doublet. We consider homogeneous properties for simplicity. Enthalpy here is equivalent to temperature. So a map view is on the left-hand side, a cross-section on the top right, and an angled view with the cooled water volume on the bottom right. After 1 year, the cold plume of the re-injected water starts to be noticeable. After 15 years, a large volume of the reservoir is affected. A characteristic tear-shaped plume towards the production well is observed. This might result in a production temperature decrease. After 30 years, the cold plume is clearly affecting the production well. Notice how the confining layers are also affected, outlined by the lime-colored lines. Heat flows from the confining layers towards the reservoir via conduction. The production temperature confirms the temperature drop after about 15 years. The drop continues until year 30 when we stop the simulation. Using the power equation, which is based on volume flow rate, the fluid density, fluid heat capacity, and the temperature difference between the production and injector well, we can see how much power we can produce. From the previous example, if we plug in the numbers, we get 8.3 megawatts of thermal power. This is sufficient to supply about 5,300 households in the Netherlands with heat. To summarize our lesson, we have seen how geothermal heat comes from the cooling of the Earth and mostly from the decay of radioactive isotopes. We have learned the 3 components needed for a geothermal system: heat, fluid, and fluid pathways. Based on the dominant heat transfer mechanism, we have classified geothermal systems such as conduction and convection dominated. Conduction-dominated systems produce heat for direct use and can be found pretty much everywhere in the world. Convection-dominated systems are used to produce electricity and are found on tectonically active areas. For any geothermal systems, we need a minimum of 2 wells to produce the hot water, extract the heat, and re-inject the cooled water back to the reservoir. We have seen an example of a geothermal doublet that can produce 8.3 megawatts of thermal power. Thank you for your attention.